All right, so we can get started here. So today is March 29th, and Module 8 has been released on sampling distribution. So now that you've completed the exam last week, we'll be moving on with the second half of the class. So today we'll be going over the sampling distribution module. Fatima, if you have any questions that you'd like to cover, I'm happy to cover any questions you might have, or I can go over the lecture slides for this next module, whichever you prefer. So today we're going to cover sampling distribution. It's a follow-up module from the basics of sampling module that we covered before the exam. And during this lecture, we will cover the 3 parts here. So there's 3 parts to this lecture. The first part will go over the central limit theorem. Secondly, confidence intervals, and finally the basics of hypothesis testing. So the central limit theorem, firstly, this is just covering some of those basics of sampling concepts that I spoke about in yesterday's section and what we covered on in the last module. The idea is to take a simple random sample from a larger population, and we can find make inferences about our population from our sample. And just to use an example, we're looking at census data here, looking at the Iowa census in the early 20th century. And we're looking at different variables, including age, gender, education, and geographic location for our participants here. And we can try to calculate what a mean education year for the population is. Since we have the data in R, we can just simply find what the population level is quite easily. And we find it to be about mu of 7. But since we didn't actually collect our census, we can actually use a sampling frame and conduct a simple random sample of participants from that larger population. So here, just as an example, we use a sample size of 10 from the larger population, and the goal is to use our sample to guess what the mean population age is. So here, we're just using a simple random sample of size 10, and we're finding amongst the sample that the mean is 6, which is not too far from the true mean population of 7. So we consider that to be our point estimate, and it's about 0.98, as you can see, away from the true population proportion. Here, we're taking another simple sample size of size 10, and we find that it's the point estimate here is 8.8 years, and if we do it again, 6.55. So now we have 3 point estimates, and we can see that there's variability amongst those 3 samples. That's what's known as sampling variability. And we can make a dot plot now for different sample sizes. So here's an example of 10 samples and looking at the sampling variability amongst these different dots as distributed. We can see here that the average of the sample means is 6.5, which is not too far from 7. Here, when we take 30 samples, we can see how the graph is changing, and it's becoming more of a mound-shaped distribution, more of a symmetrical distribution. And we notice that here the average is getting even closer, 7.35. And as we increase our sample, it's becoming more and more of that mound shape. It's appearing to be more of a Gaussian distribution, and the average is getting that much closer to the true mean population mean here. And the closest will be the highest, which is this 100,000. As you can see, a very, very Gaussian normal distribution with a very, actually this is a spot on average here of 6.98. So it shows that as we increase our sample sizes, we're getting closer and closer to that true population parameter. We also went over what's called the standard error of the mean, which is calculated as the sigma, standard deviation, divided by the square root of n. And make note that this is a lowercase n, which is the sample size, not a large case n, which would refer to the population. Here we have a standard deviation. We're just going to fill it into our numerator. On the bottom, we have a sample size of 10. So we calculate a standard error of the mean of 1.26. So to describe this distribution, we could say the distribution is centered near the mu of 6.98, and the standard deviation is approximately 1.26, which is the standard error of the mean. So that's the way we describe that distribution. As we can see here, if we increase the sample size from 10 to 100, we actually have a further reduction in the standard error of the mean because there's less variability amongst the sample, and it's a tighter distribution to the mean of 6.98 with less variability. As we had here with the sample size of 10, there was a lot more variability amongst the data set. So just to reiterate, the standard error of the mean gives a measure of how far off our point estimate x bar is from our target mu. And the sampling distribution will be roughly symmetric and mound shaped. And we can describe the center of that distribution by mu, and the variance that will be sigma squared over n. And if you just take the square root of that, we get the standard deviation of the sampling distribution, which is sigma over the square root of n. So to talk about the central limit theorem and to introduce it, the central limit theorem states that if random samples of size n are drawn repeatedly from any population with a mean of mu and a variance of sigma square, then n is relatively large, greater than or equal to 30 for most distributions. In this class, we're going to use we're going to say that if you have a sample size of at least 30, then it's going to have that distribution will take on approximately a normal distribution, with x bar being around a normal distribution with the mean of mu and standard deviation of sigma over square root of n, standard error of the mean, right? So the whole idea here behind the central limit theorem is that if we have a large enough sample size, that the sample will be approximately normal in its distribution, which is very cool. So taking any population, no matter its distribution, or repeatedly and randomly drawing sample averages from any population, we can create a new distribution that we know will be approximately normal. So even if you have a population distribution that has an irregular distribution, so long as we're taking a simple random sample of that, we would find that it's going to be approximately a normal distribution. And through the central limit theorem, we can then make inferences about the greater world around us from relatively small random samples of target populations. So as I was saying, for nearly all distributions, for this purposes of this course, we could say any data set that has greater than or equal to sample size of 30 will give us a sampling distribution that's relatively normal. And for fairly symmetric distributions, you even need less than that. So a sample size of at least 15. the actual distribution is in the population is normally distributed, then the sampling distribution of the mean will always be normally distributed despite your sample size. So just be mindful if the population which you're drawing from is already normally distribution, your sample size will be normally distributed as well. And we only need two values to describe the distribution, that being the mean, mu, and the standard deviation, sigma over square root of n, also known as the standard error. So if we convert our sample means, x bar, to z-scores, we can use our z-score transformation and calculate a z-score from our data by using this formula, x bar minus mu over the standard error, where standard error equals the squared sigma over square root of n. And we'll have a standard normal version of the sampling distribution, and the population mean will be rescaled to 0, and your standard error of mean will be equal to 1 because it's a z distribution. And that's how this looks visually. So just to reiterate, the point estimate is our best guess from our sample of a population parameter. The sampling distribution of the sample means is centered on mu and has a standard deviation of sigma over square root of n. And the shape of the sampling distribution is approximately normal for most distributions if the sample size is at least 30. So whenever you have at least 30 in your sample size, we can assume it's going to be approximately normal. So that's going over the central limit theorem, just as a summary. And next part we'll cover confidence intervals. So confidence intervals will have a point estimate, which is the single number, and the confidence interval will be this interval describing your confidence level. So it'll have an upper confidence limit and a lower confidence limit with your confidence interval. So it's a range. So for the example of the Iowa census data, our basic approach is to take each sample mean, our best guess of mu, and set upper and lower bounds based on that standard error, which will tell us how far we are from the population mean mu. So we're typically using 95% confidence intervals, and we can use the concept of the standard error to create a confidence interval of the point estimate plus minus 2 standard errors of the mean. And that will be a roughly 95% confidence interval. So here we have a sampling distribution of x bar, and here's what's illustrated as 100 confidence intervals based on x bar plus minus 2 standard errors. And as we mentioned, the standard error is sigma over square root of n. One thing to note is we don't typically know the standard error because we don't know what the population standard deviation is, sigma. So thus we actually just often use the sample standard deviation S instead of sigma as a replacement. But for now, we're going to assume that the population standard deviation sigma and that our sample with a sample size of at least 30, we can actually use our normal distribution model. And this is covering the normal distribution, but in the next lecture, we'll actually be speaking towards the t distribution if we don't know what the true population standard deviation is, and if we know what the population standard deviation is, but we don't know that the data set's normal because we have a small sample size of less than 30. So this is handling the normal distribution, what's called the z distribution, but in the next module, we'll be covering the t distribution. So we can think of the mean of a simple random sampling as a point estimate for the population mean. And as we were saying, we can then create a confidence interval using this formula. We can take the point estimate and we can add and subtract 2 times the sigma over the square root of n, which is just the standard error. And we interpret confidence intervals by saying that we roughly have 95% of the standard error can be represented by the standard deviation associated with that estimate. And 95% of the time, the estimate will be within 2 standard deviations of that parameter. If the interval spreads out 2 standard deviations from the point estimate, we're 95% confident that we've captured the true population parameter. So that is to say that, in other words, it's to say 95% of samples of this size will produce confidence intervals that capture the true population parameter, which is what it is actually describing, but it's very long-winded. So we'll usually say that we're 95% confident that the true parameter lies within this confidence interval. So we'll use the wording of we are 95% confident that the true population parameter falls within these 2 numbers. What it actually means is that some of our confidence interval capture the true population mean while others don't. And we're really talking about 95% of these confidence intervals are actually encompass the true population parameter here. So just to give an example of looking at random samples of runners, we can gather a random sample of runners and calculate an average running time of the sample of 94 minutes. And if the standard error of our estimate is 1, we can then calculate what a 95% confidence interval is just by taking our point estimate and adding and subtracting 2 times the standard error. So we said our point estimate was 94, and we said the standard error is 1. So if we multiply the standard error by 2, we'll get 2, and then we can add and subtract 2 from 94 to get a confidence interval of 92 as the lower limit and 96 as the higher limit. So to interpret this, we can say we're 95% confident the true population mean lies between 92 and 96. We can think of the mean of a random sample as a point estimate for the population mean. Using a concept of the standard error, we can create a confidence interval of the point estimate plus minus z star, which is the z statistic, multiplied by the standard error sigma over the square root of n. So z star is the number that corresponds to the particular confidence level that we want, and we can get z star using the central limit theorem and z-scores. So from the central limit theorem, we know that the mean x bar is normally distributed with a mean of mu and a variance of sigma squared over n. So that is to say it's distributed with a mean of mu and the standard error squared would be the variance. Thus, our sample mean x bar can be defined in terms of a z-score. The z of x bar is equal to x bar minus mu over the standard error. So this z-score will tell us how many standard deviations our mean x bar is from the population mean mu on the sampling distribution. And from there, we can create a confidence interval by asking how many zx bars we want to capture within our interval. So just as an example, for 95% confidence interval, the z statistic for that representative is 1.96. So that is to say that the probability of the probability density function between negative 1.96 and positive 1.96 is equal to 95%. For a z statistic representative of 99%, 99% confidence value, that's representative of 2.58. And for an 80% confidence interval, the z statistic is equal to 0.8, is equal to 1.28, sorry. So in this case, we can just plug in those z critical values, those z stars, into the formula to calculate our confidence interval. And by using some algebra, we have here a confidence interval of the probability that you have X bar. So basically you have the point estimate plus minus 1.96 times your standard error is the formula for calculating a 95% confidence interval. So by changing the level of confidence, we are, as you can see here, as we go from a 95% to a 99% confidence interval, we're encompassing more confidence, which means that our confidence interval is going to become wider as we increase our confidence, which will give us more certainty that the true population parameter is somewhere in our interval estimate. But with a higher level of certainty, there comes a wider interval estimate, which may be too wide of substantive interest. You can see that here. So you can see how, as we're changing the level of confidence, how it's affecting the different coverage rates of these different intervals. So we can see here, with the 99% confidence interval, we have 100% coverage rate of the true population parameter. But here with the 50%, you can see there's only a 0.56 coverage rate. You can see these red ones do not encompass the true population parameter. So just an example of how that affects different confidence intervals. So by decreasing the sample size, here you can see we're decreasing the sample size from 25 to 5. The coverage rate has actually stayed the same, but you can see how the confidence intervals have widened as you're decreasing the sample size here. You increase the sample size from 25 to 250, it becomes a tighter confidence interval. So to give an example of that, we can use a survey of 20 students, and we find that the mean heart rate is 65.8 beats per minute. And suppose we know that the standard deviation in the population is 7.1, and we're asking you to construct a 95% confidence interval from the sample for the true mean heart rate at Harvard. We can ask you to interpret that result as well. So we're just simply plugging those numbers into our formula. And we know our formula is the point estimate plus minus 1.96 times the standard error. So remember we said that for a 95% interval, we're going to be using the Z-star statistic of 1.96. And we're going to multiply by our standard error, which we can calculate as the standard deviation 7.1 divided by the square root of n with n equal to 20. So we find that the standard error of the mean is equal to 1.58. And by multiplying that by 1.96 and adding and subtracting that to our point estimate, which is 65.8, we'll come up with our confidence interval of a lower limit of 62.7 and a higher limit of 68.9. So that's the process of how you would calculate your 95% confidence interval from this data. To give another example is we're looking at livestock feed in this case. We're looking at a company that's developing a special feed supplement to see if it'll promote weight gain in their livestock. So the researchers report that the 77 cows were studied and they gained an average of 56 pounds with a 95% confidence interval for the mean weight gain. This supplement produced a margin of error of plus minus 11 pounds. So the question is, did the marketing department interpret the interval correctly and to explain any misinterpretations? So here we see that they said that 95% of the cows studied gained between 45 and 67 pounds. And we could say that's incorrect because we know what the cows studied gained. the 95% confidence interval refers to the population mean of cows, not the cows that were sampled. And we could say that the second statement is also false, that we are 95% sure that a cow fed from the supplement will gain between 45 and 67 pounds. That's also not correct. The 95% confidence interval refers to the population mean. Again, this statement is also not correct. We're 95% sure that the average weight gain amongst cows was between 45 and 67 pounds. That's not true. We're 100% sure that the average weight gains of the cows was 56. The 95% confidence interval refers to the population mean again. So they gave us the sample data. What our inferences are from the confidence interval is referring to the population mean, not the sample mean, which we actually have data on. So just to summarize what our confidence interval is it's saying that we are 95% confident that the true population parameter lies within our interval, or confidence interval. And finally, that will bring us to the last part of this lecture, which is the basics of hypothesis testing. So we went over some background on the first and second parts, covering the central limit theorem and covering how to create confidence intervals. And finally, that transitions us and leads us to the concept of hypothesis testing, which is going to be a big concept throughout the remainder of this class. We'll be learning many different types of hypothesis tests. So in order to have a hypothesis test, there's a number of different steps that you have to follow. The first being is that you actually have to start your claims in terms of a hypothesis, which we call the null hypothesis, abbreviated as H with a little subset of a 0, H naught, and HA, which is the alternate hypothesis. Your second step after you're stating your hypotheses is you're going to collect the data. And in statistics, we always assume that the null hypothesis is true, that there is no effect. And then we will make a decision based on the evidence. If there is sufficient evidence, we reject the null hypothesis. That is, we conclude that the defendant is guilty. If there is not enough evidence, we fail to reject the null hypothesis. That is to say that in the legal sense, we can conclude the defendant is not guilty. So to give an example, is we can look at aerobic conditioning and running amongst the general population, which is known that the mean heart rate is 69 beats per minute with a standard deviation of 6 beats per minute. And we're looking at a set of 20 students from our class in order to investigate that population parameter. So we're going to use a confidence interval for our hypothesis test. The question is first, do we think that a random sample of students from our course is a good sample of the target population, and why not? It could be a good sample of the target population, though it might consist of high proportion of highly motivated students who may differ from the population of Harvard students at large, because everyone in this course is highly motivated. So the null hypothesis we denote as H naught, and the alternate hypothesis is HA. And the null is typically conditioned to having no effect. And a hypothesis test can be either one-sided or two-sided. And these are also known as tailed. So you can have a one-tailed test or a two-tailed test. But for now, we'll focus on a two-sided hypothesis test where the null hypothesis is some claimed value for the population mean. We could say that the null hypothesis will be that the population mean is equal to the population. So here we can say that the sample population will be equal to the population mean, and alternate hypothesis will be that they're different. We're going to assume that the null hypothesis is true, and we're going to collect our data and try to see if we will reject the null hypothesis and accept the alternate hypothesis, or if we fail to reject the null hypothesis. So again, this is just how we will state our hypotheses for this given example. The null will be that the mean is equal to 69 beats per minute. The alternate will be that the mean is not equal to 69 beats per minute. And here we can just talk about type 1 and type 2 errors. Type 1 error is an error when you reject the null hypothesis when it's actually true. That's what's called alpha in statistics. So that's what's representative of the alpha value. A type 2 error is to fail to reject the null hypothesis when it's false. And that's what's called beta, or beta error. And they're also known as false positives or false negatives as well. So we can use confidence intervals to test our hypotheses. If the confidence interval does not include the claimed value, we will reject our null hypothesis. If the confidence interval does in fact contain the claimed value, you will fail to reject the corresponding hypothesis test and make your conclusions based on that. So we can calculate the 95% confidence interval here using this formula to see whether, and once we've calculated our confidence interval, the next process will be to look at our range and see if whether our null mean of 69 is encompassed within our interval or not. And as we can see here, we calculated an interval between 57.5 and 67.75. And we can see that 69 is larger than 62.74. Which means that the 95% confidence interval here does not include the null mean of 69. So we are going to reject our null hypothesis that the mean beats per minute is 69, and we're going to include that it is not 69. The mean average heart rate is not 69. As you can see here, amongst the class, it's actually a lower range than what was stated to be in the population. We can also look, however, at a 90% confidence interval and a 99% confidence interval and see how those compare to our 95% confidence interval. Remember, a 90% confidence interval will be narrower, while a 99% confidence interval will be wider. So if we're actually looking at a 99% confidence interval, that actually might encompass that 69 value, and we might have to might have had to come to a different conclusion if that was the case. So that was just an example using hypotheses tests. Another approach is to use what's called a p-value, which is most commonly reported in statistical tests. P-value, which is short for probability value, is representative of the probability of obtaining data as or more extreme than the data we actually observed, assuming the null hypothesis is true. It tells us how consistent the observed data is with the null hypothesis, and p-values can range from any value between 0 and 1 inclusive. So a small p-value will indicate the observed data and null hypothesis are inconsistent, while a large p-value indicates that they are consistent. So we say that small p-values less than 0.05 are significant, which means that we will reject our null hypothesis and conclude that the alternate is true. So you could think that if the p-value is low, the null hypothesis must go. So we use 0.05 as the basis for a cutoff, an alpha of 0.05 for our p-value, and the reason being is because it is convenient to take this point as a limit in judging whether a deviation ought to be considered significant or not. This is from one one of the founders of statistics. So it's a guideline. It's not a law in nature. It's just kind of a fundamental cutoff point that's been used in statistics for decades. So we can use an application of learning about the p-value with the Higgs particle, which is a concept taken from physics. And rather than referring to a p-value, they express their cutoff as sigma levels. So a physicist would refer to alpha of 0.05 as roughly being 2 sigma, since it corresponds to 1.96. So their cutoff is actually 5 sigma, an alpha of actually 0.0000003. So that's a very, very, very small stringent p-value. And if their p-value is smaller than that, they can then conclude that the Higgs particle exists, since the data are highly consistent with the null hypothesis of there being no Higgs particle. So a p-value of being that small is really showing that there's very strong evidence here. So just to finish up this lecture, the things to know, the main takeaways are that the null hypothesis is denoted by H naught, while the alternate is denoted by HA. And hypotheses can be either one or two-tailed. And we're going to start off by assuming the null hypothesis is true. And we can either reject the null hypothesis or fail to reject the null hypothesis. And there are two types of errors here. Alpha errors type 1 or beta errors, which are called type 2 errors. And the p-value, which is short for probability value, is the probability of obtaining data as or more extreme than the data we actually observed, and assuming the null hypothesis is true. So that's it's a quick run through this module, module 8, which is on sampling distribution. If you have any questions, I'm happy to go over any questions you might have on this module or anything else in the class. Fatima, your question was, we are going over this lecture this week, and the mission for this material is due Thursday. That's correct. So that's the timeline for this week. I can pull up the syllabus and show you that. So today is the 29th. This module was just released. So next Thursday, which is the 5th, mission number 6 will be due, which will cover this topic here. Or actually, so mission number 6. So your question is, if we're going over the same material as last week. So the last module was module number 7, which is the basics of sampling. This new module will be the sampling distribution module, which builds upon module number 7, but they are 2 separate modules, just for the purposes of the course. So this new module has additional material that the other module did not cover. If that answers your question. So so the new module was just released today, and you'll be able to watch that. And your assignment won't be due until the following week, until Thursday next week, the 5th of April. Okay. Do you have the particular questions that you want to look at? Okay, mission number 4. So I'm just gonna Just let me look that up quickly. We said mission number 4. This went over correlation analysis. Questions number 8, 9, 10, 16, 17. So, okay, we can look at this and go through them together. So, here's mission number 4. So we can go over these questions together. So question 8 says we're looking at the relationship between Obama vote, the percentage of votes in each state for Obama, and college, which is the percentage of people in each state who graduated from college. The covariance between the two variables is 30.5, and it's asking what we can conclude from this measure of covariance. So what would you say the answer is here? Between these 4 options, what can we conclude here? Do you have any idea on which of these 4 answers you would choose and why? So we're looking at covariance. So it's telling us that there's a covariance of 30.5, and it's asking what can we conclude from looking at that covariance. So the question is, what does covariance tell us between 2 variables? So does covariance tell us about the strength of a relationship, or does it tell us about the direction, or does it tell us both? And how does that differ from correlation? So covariance actually does not. Covariance only tells us about the direction of a relationship. It does not tell us about the strength of a relationship. Correlation is what's telling us whether a relationship will be strong or weak, and also the direction. So the only thing we can really know with covariance is the direction of a relationship. So knowing that, which one of these would you pick? Knowing that covariance does not tell you about the strength of a relationship. So it's not going to be the second or the third choice, because those are talking about the strength of the relationship, which you would have to look at the correlation value. So the only thing that we can tell from a covariance statistic is whether the relationship has a positive linear relationship or whether there's a negative linear relationship. That's really the only thing that we can take away from a covariance value. So since this is a positive covariance value, we know that there's a positive linear relationship between the 2 variables. If you have a negative covariance, you'd have a negative linear relationship. Yeah, this is for question number 8 that we're looking at. So I think it's random. It randomizes the choice of the answers. Um, so it so just to confirm here, we can test it's working correctly. So here it says the first choice is correct. So what's probably happening is the question, the order of the choices might be randomized. So they might appear um, in a different order on your screen, which is possible. But in this case, we're going to say that um, there's the only thing we can determine from covariance is the direction of the relationship. We would need to have the correlation in order to speak to the strength of the relationship, whether it's a strong relationship or a weak relationship. And remember that the closer the correlation value is to 1 or -1, the stronger that relationship is. And the closer it is to 0, the weaker it is. So let's see, we can take a look at the next question. Oh. Okay, so question number 9. This question says, you find out the variance of Obama vote is 88.7 and the variance of college is 28.4. Note also that the covariance between Obama vote and college is 30.5. What is the correlation between Obama vote and college? And round all your intermediate calculations and answer to 2 decimal places. So this question is asking us to calculate what the correlation value is from the covariance, and the variances. So it's just plugging in to the equation that we have for you. So we can attempt this question as well. You know how you would answer this? Well, I could pull up the formula and we can work on it together. So if you look at the correlation analysis lecture notes, it's on slide number 74, and I'll just show you what that looks like. Yeah, so you have the formula, that's right. The correlation is equal to the population covariance of X and Y divided by the population standard deviation of X times the population standard deviation of Y. So you have the formula there. So we could go back to the question and try to work on that together. So how would we calculate this? How would we calculate the answer here on what the correlation is? They give us all the information we need, and now we just have to plug it into the formula and calculate that, right? So they gave us the population covariance, right? And they gave us 2 variances. And the denominator is the variance of X times the variance of Y multiplied together. So we can work on calculating what that correlation is. So you can calculate what the denominator is by multiplying the two variances together. 88.7 times 28.4. And that will be your denominator. And your numerator will be the covariance, right? And that should give you so were you able to come up with an answer here? So if you look at the formula, just remember it's looking at standard deviations, and they're giving us the variances. So what we would have to do is we have to take the square root of the two variances that they give us, and then we would multiply those together, and that would form the denominator. And then the numerator will be the covariance, and then we can calculate correlation from that. So you did 30.5 divided by the square root of 88.7 multiplied by square root of 28.4, and you got 0.61. And I think that's also what I got as well. So we came up with the same answer. So that's how you would answer that question. We could check if that's right. And maybe we'll cover one more question in the last 5 minutes. Do you have a preference of which question you want to cover next? 10, 16, or 17? We could do, you want to do question number 10? So we can see here, question 10 says, what can you conclude from this correlation in terms of strength and direction? So if we're saying that our correlation is 0.61, what phrase here will describe this correlation in both strength and direction? This is a positive 0.61 correlation. And remember that the correlations closest to 1 are strongest, and correlations closest to 0 are the weakest. So how can we describe a correlation of 0.61 amongst these 4 statements here? Yeah, so you said it's fairly strong and positive. That's what I would say as well. Yeah, I agree. Since it's 0.61. Maybe we could try covering one more question number. See if we could try to get through 16, 17. So question 16 says, another way of understanding the spread of IQ data is to use the empirical rule. The distributions of IQ scores across the states in the US South is roughly mound-shaped. What is the interval in which 95% of the IQ scores lie? So this is based on the previous question. which is looking at the IQ values in 13 states here, with a mean of 98.1 and standard deviation of 2.12. So if we're looking, if you remember from 95% of, in the empirical rule, we're looking at plus minus 2 standard deviations of the mean. So here we say that the mean is 98.1 and the standard deviation is 2.12. So in order to figure out what the 95% interval would be, we would multiply the standard deviation by 2. So 2.12 times 2 is 4.24. And then we'll add and subtract that from 98. So 98.1 minus 4.24 will be around 94, right? And if we add 4.24 to 98.1, we'll get 102, right? So we just look here, and that's how we answer that question. And the next question says, using the above set of 13 states, what would the mean of the IQ variable become if you were to subtract 98.1 from each value in the IQ set? So in order to answer this question, what do we think the answer to this would be? So we said no change. So let's take a look at the answers and let's see how we did. Okay. So we answered questions 9 and 10 correctly. And then we did 16 and 17. Yes, the answer is 0, because here we're looking at the mean. So if you're subtracting out the mean from all those values, from each of those values, you would come up with a mean of 0 just by looking at the average formula. If we were talking about the standard deviation, that would not change. The mean would. So that's how you answer that question. So I'm glad we were able to go through this lecture and cover some of the questions you had from the previous mission. If you have any more questions, feel free to follow up with an email, and I will see you guys all next week, and hope you guys have a good week and enjoy this material, and have a great weekend.